Okay, so imagine you're building something new, right? An app, maybe a service, something that needs to handle, well, potentially a lot of traffic. And you're faced with this huge landscape of programming languages, frameworks, and the big question hits you. How do you choose the right tools? Especially when you need performance, speed, and a massive scale. It's a tough spot. It really can make or break things.
It absolutely is, yeah. And that's exactly why this deep dive is, I think, so useful. We're not just talking theory here. We're actually putting two real heavyweights, Node.js and Golang, go head to head. But in a proper production-ready environment, the mission really is to uncover how they actually perform, find the bottlenecks, maybe have some of those aha moments when they're really pushed hard.
And what's great about the source material we're digging into today is, well, it comes from this super detailed practical benchmark done by a seasoned DevOps engineer, right?
Yeah, exactly. This wasn't just some quick test on a laptop. No, they deployed both apps to a full production-ready Kubernetes cluster running in AWS and using the latest generation EC2 instances, too. So, yeah, this is definitely where the rubber meets the road.
Okay, so let's unpack that. We've got Node.js using Express. I mean, that's super common. And then Golang using its standard library, which is known for being pretty efficient. So yeah, this deep dive is going to get into the real nitty-gritty details of how they compare.
And what's really fascinating, I think, is the focus on practical metrics, things that really matter in production. We're looking beyond just, simple requests per second. We're talking CPU usage, memory usage, actual application availability, like did the request time out, even things like CPU throttling, which Kubernetes can impose, and network pressure too, tracking how many bytes each app is sending and receiving, and even considering things like keep alive connections, which can really boost efficiency by reusing connections.
Right, those details matter. So, okay, part one, the first test. This was the bare bones web application test, looking at raw performance, yeah.
That's right. Set the stage. Both applications deployed, ready for load. No database involved yet.
And how did they actually run the test? What was the method?
Okay, so they used a Kubernetes job with 20 replicas to generate the load, and they gradually ramped up the number of clients hitting the applications stage by stage, basically until things started breaking. They had a 60-second interval between each load increase and, importantly, a strict 1-second timeout for each client request. That timeout directly impacts what they measured as availability. If it takes longer than a second, it's considered unavailable for that request.
Got it. So Node.js performance, what did we see right from the start?
Well, straight away, Node.js was using more CPU, even at lower loads. And its latency, the time taken to respond, was significantly higher compared to Go. Actually, the source mentioned its performance was kind of similar to Python Django, which they tested before.
Interesting comparison. What about memory and data?
Also higher for Node.js. It used more memory. And kind of interestingly, it sent more headers by default with each response, which just means it was transmitting a bit more data over the network for every single request.
Okay, but the real story happens under pressure, right? What happened when they really cranked up the load on Node?
Right, this is key. They found something they called the 60% CPU wall. When Node.js hit about 9,000 requests per second, its CPU usage climbed to 60%. And then it got stuck there.
Stuck, like it just wouldn't use more CPU even if it needed to.
Pretty much. For the rest of the test, as they increased the client load further, the CPU usage for Node just hovered around 60%. It didn't go higher. But what did go up was the request latency. So requests took longer and longer, performance degraded, and a lot of requests started hitting that 1-second timeout. You could see the availability dropping right off in the graphs.
And they made sure it was a fair test, like using async correctly in production mode.
Oh yeah, definitely. The author noted they used async functions properly, so no blocking operations were holding things up. And they explicitly set Node.env to production. This 60% wall seems to be, related to how its single-threaded event loop handles really heavy load. It processes what it can, then queues the rest, leading to that latency jump.
Okay, so Node hits this 60% CPU wall around 9K requests. Meanwhile, what was Golang doing under the same conditions?
Golang was a different beast altogether. In the same setup, it managed to handle somewhere around 70,000 to 80,000 requests per second, significantly more.
Wow, okay. That's a huge difference. But how did it fail eventually? Did it hit the CPU wall too?
No, its failure mode was totally different. The Go standard library, it doesn't have built-in rate limiting like some frameworks might, so it just kept accepting and trying to process all the incoming requests. It didn't slow down gracefully. It spun up more coroutines, cached requests, until basically It ran out of memory. It hit 100% memory usage, and then Kubernetes stepped in and killed it. Out of memory kill. Just stop the process.
Right. So 70, 80,000 requests for Go versus maybe 9,000 for Node.
Yeah.
That's a pretty stark difference right off the bat. But like you said, it's not just the number. It's how they fail. Node kind of degrades, latency spikes, Go just explodes when it runs out of RAM.
Exactly. And this points to, well, fundamentally different bottlenecks, doesn't it? Node hits the CPU ceiling, but it sort of degrades gracefully, if you can call it that. Latency increases. Golang pushes the hardware, especially memory, right to the absolute limit and then crashes hard. And this tells you a lot about their internal architecture, how they manage concurrency, how they handle resources under extreme load.
Yeah, and it suggests different ways you'd need to scale them too, right?
For sure, like the engineer running the tests suggested that for Node.js, because the bottleneck is that per process CPU limit, just increasing the number of replicas running more copies of the Node app would probably be more effective than using Node's built-in cluster mode, which tries to use multiple cores in one process. More separate processes seems the way to go for Node in this scenario.
Okay, that makes sense. So that first test was like a pure speed trial, raw power. But most real apps, let's be honest, they need to talk to a database, right? A storing state is crucial, blog posts, user data, product inventory, whatever it is. So how did things change when they added that persistence layer? Did it level the playing field?
Right, that was the crucial second test. More realistic for most use cases, the setup involved a POC rest with some JSON data. The app would generate a unique ID, a UUID, for a device, let's say, and then save that ID to a Postgres database, a relational database.
Okay, standard stuff. And the database setup.
They used an open source Postgres Docker image, pretty standard. Migrations were handled by an init container. And here's a key detail. They set a maximum connection pool size of 20 for both applications. That's a common real-world constraint. You don't want unlimited database connections.
Yeah, pool size is always a factor.
Yeah.
Did they use good database drivers?
Yep. They noted that for Node.js, they picked one of the fastest available Postgres drivers to make sure the comparison was as fair as possible, minimizing any driver overhead.
Good. So with the database in the mix, what happened? Did Go still dominate?
Well, initially things looked a bit closer. The latency just to do the database insert operation was actually more or less the same for both Node and Go. And the overall request latency was also pretty close at the start.
Ah, okay. So the database did become a bit of a bottleneck then.
To some extent, yes. But the CPU and memory usage patterns, they remain very different right from the beginning. They follow the same trends we saw in the first test without the database. And very quickly, that connection pool hit its maximum size of 20 connections for both applications. That became a shared limiting factor.
Okay, so the pool maxed out. What happened to Node.js under load with the database? Did it still hit that wall?
It did. Again, around 4,000 requests per second this time, a bit lower because of the extra database work. Node.js reached that familiar 60% CPU usage. And just like before, it started to degrade. Latency went up, requests started timing out more often. So about 4,000 requests per second was its effective maximum in this test, with the database involved.
Right. Still hitting that 60% ceiling, just sooner. And Golang with the database, did it also hit a wall, or did it run out of memory again?
It followed its pattern, too. Around 7,000 requests per second, Golang seemed to get stuck in terms of throughput, but its memory usage just kept climbing and climbing as the load increased further. Just like the first test, the failure mode was memory exhaustion. If they'd kept pushing, it would have hit the limit and gotten killed by Kubernetes again.
Okay, so this is really interesting. Even when you introduce a common bottleneck like a database connection pool, the fundamental characteristics, the failure modes, they persist. Node still hits that 60% CPU limit and slows down. Goso pushes until it runs out of memory.
Exactly. It's fascinating, isn't it? The database adds pressure, sure, and it lowers the overall numbers for both. But how they react to that pressure, how their resource consumption behaves, it stays remarkably consistent. It really reinforces those inherent differences in how these runtimes manage concurrent tasks, how they scale internally, especially around things like database connections.
Yeah, it's clearly not just about which one is faster on paper. It's about their whole personality under load. So wrapping this up, what are the key takeaways for you listening? For the developer, the architect, trying to make these choices?
Well, I think the first clear takeaway is the raw performance difference in these specific benchmark scenarios. Go consistently handled significantly more requests per second than Node.js, both with and without the database interaction. That's pretty clear-cut from this data.
Right. The numbers are stark. But maybe more important are the failure modes.
Absolutely. Understanding how they fail is critical. Node.js tending to bottleneck on CPU around that 60% mark in this setup, leading to increased latency and degradation. While Golang tends to push memory much harder, ultimately leading to those abrupt out-of-memory kills when it hits the limit. These aren't just technical curiosities, they have real architectural implications.
Yeah, how so? How does knowing this help you design better systems?
It directly informs your scaling strategy, right? As we discussed, for Node, maybe scaling horizontally with more replicas makes more sense than trying to optimize within a single process's CPU limits. For Go, you need to be really mindful of memory allocation and perhaps implement your own rate limiting or circuit breaking to prevent it from overwhelming itself and crashing. It also affects resource provisioning, how much CPU versus memory you allocate in your Kubernetes deployments or other environments.
And it really highlights the value of this kind of testing, doesn't it? Doing it in a realistic, production-like environment.
Totally. Abstract discussions or simple hello world benchmarks only tell you so much. Seeing how these systems behave under realistic load, on real infrastructure like AWS and Kubernetes, with database connections, that gives you far more actionable insights. And credit to the engineer who ran this, they provided so much detail and even invited pull requests for improvement.
Yeah, that transparency is great. So it really boils down to understand not just which is faster, but maybe more like how do they behave under stress and what's their scaling personality.
Precisely. This kind of granular data encourages us all to think critically, to question the defaults, to really consider how our choices, the language, the framework, the standard library, truly impact how our application behaves when things get tough. It just shows there's always more to learn about optimizing for the real world, not just the lab.
So thinking about these really distinct performance traits, these different ways they fail, what new questions does this raise for you, the listener? Especially when you're designing systems that need to be resilient, that need to scale as your application grows and the demands just get more and more intense. Something to chew on.